Hello. By the end of this video, you will be able to interpret sampling theorem or the Nyquist sampling theorem and its application in analog to digital conversion. So both sides, analog to digital or digital to analog conversion. So this is a very straightforward theorem, and the theorem says that if you have a signal which has bandwidth of W, which is a band limited signal, which means that if its Fourier transform is zero outside of this assumption, simply means that your signal is zero outside of the bandwidth of above frequencies above W. So if this is frequency domain, which means that this signal XF is zero for any frequency above W. So after W, X of F for all frequencies in this area is 0, and for all frequencies which is smaller than here is 0. So this signal in frequency domain should not have any components above this frequency W or below this one. In that case, we call it band limited signal with a bandwidth of W. For such a signal, which can be applied approximately to all signals in nature. For instance, for your voice signal, for telephony signals, this frequency is about 3.4 kilohertz. For video is like several megahertz and so on. Such a signals, we could take a number of samples per second from the signal in time domain, and using those samples we could perfectly reconstruct the signal, the original continuous time signal. So this theorem, which was proven by Nyquist in 1923, it says that the original signal x of t could be calculated using samples of the signal taken at equidistances in time. So if this is time, and you take a sample at time t equals 0, then you take another sample at time ts, then another sample at time 2ts, etc., and also samples at time minus ts, and so on. So the value of the signal at this point is x of 0, x of ts, x of 2ts, etc. If you look at this equation, you see that this summation is only calculated, this value, this side, is only calculated using the samples of the signal at multiple integer factor of nts times. So the samples of the signal, if this theorem is true, the samples of the signal are enough to calculate the signal at any arbitrary time t. What does mean that this theorem? It means that I don't need to have the value of the signal at all values of time t, either t be any number, any arbitrary real number. So this signal, which is multiplied by my sample, and then these signals are added together, and it's a sync one. So you have learned about these signals as system in your previous courses. So this theorem specifically says that this perfect reconstruction, this equality is true if Ts, or if the interval of sampling, if the time duration between the samples, this is Ts and this is Ts, because I'm taking uniform sampling every t seconds, provided that Ts is less than 1 over twice the bandwidth, then this signal reconstructed is exactly identical with the original input signals. So this 1 over 2W is the largest period of the sampling you can take, and is called Nyquist rate. So sampling theorem says that provided that the sampling frequency is greater than twice the bandwidth, you could perfectly reconstruct your signal. And this theorem says that any band limited signal can be fully reconstructed, fully recovered from its samples, its set of samples. So if you have these samples for all integer values of n, then you could calculate x of t. So what does mean? It means that if you give signal x of t to a samplers, so you take samples at time t equal to nts, and if you have the sequence of x of nts, using these samples you could give it to a reconstruction system and get your signal x hat of t, and this x hat t is equal to the input. So if you do process the samples instead of the original signal, you're okay, because these x and ts contains all necessary and sufficient information for x of t. In other words, the information contained in the sequence of samples is sufficient to know the value of x of t at any arbitrary time instance. So there is no loss of information. So this theorem perhaps has been the most important theorem proved in last century, which has led into development of telephony systems, communication systems, computers, and so on.